So now that we've spoken about the basic principles underlying the phenomenon of magnetism, I will now discuss the applications of nanomagnetism. A very major chunk of applications of nanomagnetism lies in the magnetic data storage industry. As you know, there's an ever-increasing demand for higher areal density, which is given in gigabits per inch squared, that is 10 to the power 9 bits per inch squared, or terabits per inch squared, which is 10 to the power 12 magnetic bits per inch squared. Now, the problem is that as you keep shrinking the size of an individual bit, there is a certain point at which the superparamagnetic limit will be reached. So what is the solution to that? One can develop materials with higher anisotropy constants, known as high K materials, or develop new recording technologies. The other area in which a lot of research is being done is spintronics, which is a field which uses the spin as well as the charge of the electron for data storage as well as processing. So because you're combining both functionalities in one device, the size of a typical element or device will shrink, and the condition here is the size of the element should be smaller than the spin diffusion length, which is typically the length scale over which a spin which is oriented in a particular direction loses its coherence. The third area of application that I will be discussing is biomedical applications, in which we'll talk about drug delivery, magnetic hypothermia, and MRI contrast enhancement. So, MRI, as you know, is a technique that is used in medical diagnostics. It stands for magnetic resonance imaging, and this is a technique using which one can diagnose tissue that is in some manner pathological or diseased. So what is the principle behind MRI? First, I'll discuss that, and that will bring us to how nanoparticles can help enhance the contrast that is available in magnetic resonance imaging. So, as you know, that the body is made up largely of water. So there are 2 hydrogen atoms and 1 oxygen atom per water molecule. So if you look at the hydrogen atom, then the proton has a magnetic moment of 9.27 times 10 to the power minus 7 joule per Tesla, and it is the magnetic moment of the proton which is being used in magnetic resonance imaging. So if a field is applied, for example, in the direction of B naught, let's say it's the Z direction, then this field causes the magnetic moment to precess around it along, so that it's the tip of the vector magnetic moment lies along this path, the circular path, and the projection of the proton's magnetic moment on the field axis remains constant. This precession frequency is known as the Larmor frequency, and it is proportional to the applied magnetic field B naught, and gamma is a factor which is 2.6710 times 10 to the power 8 radian per second per Tesla. So for B naught of about 1 Tesla, the frequency that one requires is about 42.5 megahertz. So at a field of 1 Tesla, of a total of, if let's say I have n hydrogen atoms in the body, then the number of hydrogen atoms with their spins aligned in the direction of the field at body temperature and a field of 1 Tesla is 5 in 1 million. So 5 times 10 to the power minus 6, which is an extremely small number. But if you consider that 1 millimeter cubed of H2O contains 6.7 times 10 to the power 19 water molecules, then the number of hydrogen atoms that have their spin aligned in the direction of the magnetic field becomes quite large, namely 3.35 times 10 to the power 14 per millimeter cubed of water. And this large number can then be used for medical diagnostics. So even though the moment of the hydrogen atom is extremely small, but by virtue of the fact that you have such a large number of water molecules in the body, the total magnetic moment becomes something that is measurable. So the way MRI is done is that one has a DC magnetic field applied, say here, in the vertical Z direction, and a AC magnetic field of RF frequency, so of the frequency that we calculated, the Lamour frequency, which was about 42.5 megahertz. This is applied perpendicular to it, and this RF field causes the magnetic moment to precess around B0, and ultimately it causes the magnetic moment to flip in the horizontal plane. And this change in the magnetic moment can be measured as a function of time. So in the z direction, one finds that the magnetic moment increases and then reaches a constant value, and this change in the projection of the magnetic moment is controlled by a time constant t1, and in the xy plane its behavior is oscillatory and is controlled by a time constant t2. So the principle of imaging is the following, that different tissues have different relaxation times. So the values of T1 and T2 are different for different tissues. For example, bone will have a different relaxation time. The hydrogen atoms in fluid, for example, fatty tissue, may have a different relaxation time. So if one does a T1 scan, fluid containing tissue appears dark and fatty tissue appears bright. On the other hand, in the T2 scan, that is if you're measuring this time constant, then fluid containing tissue appears bright, and the converse is true for fatty tissue. So the point how you can make use of this is the fact that damaged tissue naturally develops edema. It becomes swollen. That means its fluid content becomes higher. So that using T1 and T2 scans, one can distinguish pathological tissue from normal tissue. So having discussed how MRI is actually done, let us now come to what is the role of magnetic nanoparticles. Research in this field has shown that T2 can be significantly changed by inhomogeneities in the local magnetic field. And these inhomogeneities in the local magnetic field are controlled by embedding magnetic nanoparticles in cancerous tissue. This is facilitated naturally because cancerous tissue or tumor sites have an increased natural selective uptake of magnetic nanoparticles. First, because the capillary endothelium of tumor cells, that is the layer lining the tumor cells, the capillaries of the tumor cells are disordered. They are disorderly in nature, so that tumor tissue has an increased permeability as compared to normal tissue. The other factor is that tumor cells have a damaged or defective lymphatic drainage system, which is a system that basically sort of flushes out or cleanses biological tissue. And because this is damaged, there is increased retention of magnetic nanoparticles in tumor cells. So because of these two factors, there is an increased selective uptake of magnetic nanoparticles in tumor cells. So what one can do, if one can inject these nanoparticles, of course they have to be biocompatible, into some artery which is supplying a tumor, or place them directly at a tumor site, then they will be retained there. Okay, once they're retained there, what they do is that they create a local magnetic field around them because they're magnetic. And they can be superparamagnetic or paramagnetic nanoparticles, and they create a tiny magnetic field around them, delta B0. And this delta B0 affects the relaxation time T2. So T2 for areas where there is a concentration of magnetic nanoparticles will be different than from the surrounding tissue. And in this way, because the magnetic nanoparticles are concentrated at tumor sites, one can look physically at the size of the tumor and find out its location. So MRI is most commonly used in biomedical diagnostics, and it is now a commercially available technique. The contrast agents that are most commonly used are spions, which are superparamagnetic iron oxide nanoparticles of diameter larger than 50 nanometers. These have been produced commercially, and these are the commercially registered names: Lumerum and Endorum. Lumerum consists of silicon-coated magnetite nanoparticles of diameter about 300 nanometers, and endorum are dextran-coated magnetite nanoparticles of diameter 150 nanometers. The other class is euspions, which are ultra-small superparamagnetic iron oxide nanoparticles. These typically have diameters less than 50 nanometers, and the registered names here are Cynorem, Combidex, and Clariscan. However, you will note that all these medically available diagnostic materials, these are of magnetite, and currently research is going on to use materials which are mixed metal ferrites, for example transition metal doped zinc ferrites, and these are being researched for applications as MRI contrast agents. The issues here are that one has to deal with are their cytotoxicity, making them biocompatible, and at present magnetite is the only magnetic material in nanoparticulate form that is approved by the US Food and Drug Authority, the FDA, for use inside the human body.